Is that okay?
Yes, go ahead, please. Thank you.
Okay. I will discuss the corona, ask the question, what is it? And let me start by presenting the standard picture that our community has about the corona. The corona, as we all know, is the place where the hard X-rays are produced in black hole X-ray binaries. And then after I do that, I will point out some possible problems. The standard picture that we have is based on two strong beliefs that our community has. And belief number one is that the power law X-ray spectrum is with exponent gamma for the photon number in black hole X-ray binaries is produced in the corona by inverse Compton scattering. I give two examples of references. I have no objection to that, but wait a little. The picture here is that this soft photons from the Shakura-Sunyaev disk get into the hot inner flow in the corona and get upscattered and produce the spectrum. We have very successful models for this. Now, for timing, the hard X-ray photons are observed to come later than the softer ones. Thus, there is a time lag. And belief number two is that the time lag of the hard X-ray photons with respect to the softer ones is caused by propagating fluctuations in the accretion flow. And you heard from Phil just a few minutes ago why he prefers that. I have no objection to this. Back to the schematic. So the hot corona has a temperature gradient. It's hotter here than there, and therefore propagating fluctuations produce harder spectra later on, and that explains. It's a natural. It's a very beautiful explanation. I think propagating fluctuations definitely happen in accretion flows. We cannot imagine a smooth flow, so fluctuations will happen, and all that is fine. But the two mechanisms, Compton scattering for the creation of the spectrum and propagating fluctuations for the time lags, do not talk to each other. In other words, no correlation is expected between T lag and the power law spectral index. I'm waiting for Phil's and Julian's paper to study, but at the moment I haven't seen anything. So why that? There's no correlation expected because gamma, the spectral index, is determined from the properties of the corona, optical depth and temperature, while T lag from the flow time scale and the origin of fluctuations. However, we have found, Pablo, Rig, and I found that there is a correlation, and a very nice one. Here it is. For GX339-4, from the look at the x's, the lower part of the hard state, upper part of the hard state, and hard intermediate state, and the blue dots are our models, which I will explain shortly. Nice fit. We have explained this correlation by Compton scattering in the outflow. In other words, we have extended the corona to include the outflow. The Comptonization determines the spectral index gamma, and the size of the outflow determines the lag. And because both are produced by the same mechanism, it's natural that they are correlated. The outflow in black hole X-ray binaries is generally ignored. I will try to convince you that this is totally wrong. In my opinion, the outflow must be a part of the corona in black hole X-ray binaries, and I hope to convince you of that. You have already seen the explanation of the correlation T lag versus gamma that I showed earlier. It was naturally explained by extending the corona to include the outflow. And I will discuss a few more correlations, which are also successfully explained quantitatively with the extended corona. So again, the schematic. From the hot inner flow, out comes the outflow, and this outflow, notice, engulfs the hot inner flow. So Comptonization, since the outflow engulfs the hot inner flow, the Comptonization in the outflow is unavoidable. In other words, most of the photons that enter the hot inner flow cannot escape without traveling through the outflow and being scattered there. In the scattering process, the photons forget their previous history, and thus it is the last scatterings that determine the spectrum. The outflow, in other words, fixes the observed power law gamma. Generalization of the T-lag versus gamma correlation to all sources. It's not, this correlation that I showed you before is not a peculiarity of GX339-4. All sources do more or less the same. And here is the result of 13 sources, T-lag versus gamma. I don't like this. It looks like a scatter diagram, despite the fact that we fitted a line. However, if you ask the right question, you may disentangle this scatter diagram. We ask the question, how do low inclination sources behave, and how do high inclination sources behave? That also Phil showed earlier about the QPO. They behave differently. And indeed they are different. High black and low black and high red bound all this scatter that I showed you before. So high inclination down here, low inclination up here. And in the paper that we published, Pablo and I, Pablo divided the sources into three categories: low inclination, intermediate inclination, and high inclination. And we fitted with the same model, with the same outflow, all three of them. Time lag versus Fourier frequency correlation. I want to stress that a parabolic outflow, which is what we use, explains naturally the correlation between time lag and Fourier frequency. That is the power law that we see that the time lag goes like nu to the minus 0.8. Non-parabolic outflows, for example, conical, do not work. And here are the observations. Phil showed them also by Pottsmith et al. And this is a nu to the minus 0.8. Let me explain how an outflow model can reproduce the nu to the minus 0.8. This is a schematic of the outflow. It consists of three regions with radii R1, R2, and R3. And the time lag in each one is T1, T2, and T3. And as you go up, the time lag increases. We all know that Comptonization acts like a filter which cuts off the high frequencies. So if the scattering happens here, then all the frequencies above 1 over T1 are cut off. If the scattering happens here, then all the frequencies above this frequency are cut off. And if it happens here, all of these. As a result, you get a power law. I want to stress that in a parabolic outflow with optical depth of order unity, it is equally likely for the photons to scatter here or there or there or anywhere. Equal optical depth in every decade of distance. And here is the nu to the minus 0.5 result from our model. In 2015, Altamirano and Mendes published the data shown here, the average time lag versus cutoff energy, and literally days after we saw the preprint, we wrote our paper because we had all the calculations ready and we simply produced the line. So the time lags correlate not only with the power law, but also with the cutoff energy. Another observational constraint that's very old, Tom Macarone showed it for the first time in 2000, that the autocorrelation function decreases in width with increasing photon energy. Equivalently, Novak et al. Showed that the high-frequency power spectrum flattens with increasing photon energy. And here are the results. We fitted them quantitatively. I don't have time to explain that. Type B QPOs. Stevens and Nutley proposed that the type B QPOs in GX339-4 are due to a precessing jet. Here is the variation of the power law index, 6% variation. And since we predict that the outflow model has a variation of gamma with viewing angle, as the jet precesses, you should see this amplitude variation. And we again quantitatively reproduced the variation and the inclination angle. So this is the variation in gamma. This is the variation, the uncertainty in the inclination angle. And indeed, a model fits nicely. So last slide. I'm running late, but last slide. I really find it amazing that this simple outflow model can explain quantitatively so many correlations. It's unbelievable. It's really a truly simple phenomenological model, yet it does so well quantitatively. The values of the parameters of the outflow are reasonable and the same for all the correlations. Two parameters: optical depth along the jet between 1 and 10, radius between 10 and 1000 Rg. So I urge competing models to try to fit these correlations. They really constrain models. Thank you very much.
All right, thank you, Nick. It's really amazing that so your fitting model has only two parameters?
Yes. And always, in all these correlations, the parameters vary in that region, in these regions.
Okay. Any questions from, okay, someone raised their hand.
So I should, how do I stop sharing? Okay.
This button. Well, okay, I don't seem to see any questions, but I do have, there's one question, okay.
Are there other observations that you suggest to do, also maybe including multivariate observations to support your model?
Okay. I will be a little obnoxious now. All self-respecting models should make predictions. And our prediction is that during the rise of the outburst, say in GX339-4, if we catch it early on, the break frequency in the radio spectrum should increase with time. So it's a prediction. It's not easy. So you have to arrange radio telescopes to measure the low end and high end and find the break frequency. But nevertheless, it's a prediction.
Okay, thank you.
Here I have a question for Nico.
Yes.
This is Dimos.
Dimos Kazanas, yes.
So optical depth 10, that's fairly high. Is it fully ionized, the gas?
Yes, because the outflow comes from the hot inner flow, which is at 10 to the 9
centimeters.
Yes. So
10 to 9 degrees, you mean?
10 to 9 degrees, yes. All models have 100
okay,
kV.
All right, fine.
Corona. So the outflow
the point is that in general, these winds, they're not necessarily limited at the how many Schwarzschild radii was the puffed up. But of course, the puffed up component depends also on luminosity. As Phil showed earlier, schematically, as you increase the luminosity, the size of the puffed up component decreases. So, but that's okay. I mean, I don't think that this has any problem. What we have suggested in the past is that this wind extends actually all the way to the outer edge of the accretion disk, simply because it's driven magnetically, and magnetic driving doesn't care if all you have to do is ionize, not neutral. And that's how we could explain to some extent the absorption features that we see. Well, not as much in galactic sources, because there's high ionization. The galactic sources are highly ionized, and we see the outflows at very low velocities. Of course, the proposal we have is that these outflows continue all the way to R equals 3Rg or whatever it is. And of course, they're consistent with what you have there. I'm a little bit wondering about the high optical depth that you need. But optical, the tau Thomson depth, 10. Well, okay, that's okay. One has to have in mind, of course, with such high optical Thomson depth, that the mass flux that you have in the wind is much higher what you need to fill the black hole.
Much higher than what you need to fit?
To produce the X-rays from that by accretion.
Why do you say that? No. If the outflow velocity is not high, then you don't have that much mass.
Well, it has to be at least the escape velocity from the system.
Yes, of course.
So at 3Rg or 10Rg, that's half the speed of light. But anyway, it doesn't matter. I mean,
okay.
This is consistent with the work we are doing too, but we actually have most of the mass flux escaping at large radii, and that people who do spectroscopy find that. But nonetheless, your picture seems to be fitting rather well with ours, except what we suggest that there is mass flux at higher radii too. It's not necessarily be confined to the 10 or maybe 100. Your puffed up region goes as high as 100, right?
But we do see winds from the Sakura-Srinaev disk from further out.
Yes, of course we do. Well, of course. Obviously, it's not Sakura-Srinaev, because that would not,
whatever it is. Yes,
we would not do such winds. But nonetheless, thank you. I really appreciate your model. Yes, thanks.
All right, maybe we should. We're running late. Maybe I'll one more question, maybe from Javier.
Hi, very quickly, is this outflow acting as extended corona? And if so, it will predict a flat emissivity profile, so flatter illumination of the accretion disk. But that's in contradiction with what we typically observe, right? We see these very steep emissivity profiles. Have you thought about that?
No, it is in our plans with Pablo to study reflection, because scattering in this outflow will send photons back to the disk, and therefore we can do that. We haven't, so yeah. Maybe we can exchange emails on that. Please send me an email and I will try to answer. But we haven't done any calculation yet.
All right, thank you very